She entered the alien school classroom until her knowledge of the universe shocked everyone. Then they stopped treating Earth education as primitive and started questioning whether humans had access to information sources that shouldn't exist yet according to the galactic technological timeline. Let me tell you about the day I learned that human education includes philosophical frameworks and scientific theories that most species don't develop until they've been spacefaring for centuries. Spoiler alert, the primitive species from the backwater planet somehow knows things about quantum mechanics and cosmology that our most advanced researchers are still debating. My name is Professor Thelm Vorik, Senior Instructor of Universal Studies at the Korvathi Imperial Academy, and I have taught advanced astrophysics and cosmology for 34 standard cycles. I have educated over 6,000 students from 43 different species, published 89 peer-reviewed papers on fundamental physics, and served on the Galactic Council's Scientific Oversight Committee for 12 years. Point is, I know education. I understand pedagogical frameworks across multiple species, what constitutes advanced knowledge versus basic understanding, what separates sophisticated comprehension from simple memorization. I can assess a student's education level within the first class session based on their questions, observations, and conceptual frameworks. I thought I had seen every variation of scientific understanding, from species that barely grasped basic mechanics to those with intuitive comprehension of relativistic physics. Then a human student enrolled in my advanced cosmology course, and I discovered that Earth's education system apparently includes concepts that most civilizations don't encounter until they've been exploring the galaxy for millennia. The semester began normally. 23 students, various species, all qualified for advanced study based on prerequisite coursework and entrance examinations. Most were from established spacefaring civilizations with centuries of scientific tradition. A few were from newer species still developing their understanding of universal mechanics. And one was human. Kira Chen, exchange student from Earth, a planet that had only achieved faster-than-light capability 15 years earlier and was still considered scientifically primitive by most galactic standards. She was approximately 163 centimeters tall, slim build, with dark hair pulled back in practical style, brown eyes behind corrective lenses that seemed quaint given that most species had solved vision problems genetically millennia ago, and this notebook, an actual physical notebook with paper and pen, that she carried everywhere instead of using standard digital recording equipment. Welcome to Advanced Universal Mechanics, I began the first session. This course covers fundamental questions about the nature of reality, the structure of spacetime, quantum foundations, cosmological evolution, and the mathematical frameworks that describe universal behavior. Prerequisites include graduate-level physics, advanced mathematics through tensor calculus, and demonstrated comprehension of both relativistic and quantum mechanical principles. I paused, looking at the assembled students. This is not introductory material. I assume you all have solid foundations in fundamental physics. If anyone feels unprepared, now is the time to transfer to a more appropriate course level. No one moved. Good. I launched into my opening lecture, covering the course structure and beginning with what I considered a moderately challenging warm-up topic, the interpretation problem in quantum mechanics. Quantum mechanics works perfectly as a predictive tool, I explained, displaying mathematical formulations on the projection screen. We can calculate probabilities with extraordinary precision. But the question of what quantum mechanics means, what's actually happening at the fundamental level, remains deeply controversial. The Copenhagen interpretation suggests observation collapses probability waves into defined states. The many worlds interpretation proposes that all possibilities occur in parallel universes. Pilot wave theory suggests hidden variables determine outcomes. Each has mathematical support and philosophical implications. I looked at the class. Thoughts? How do you interpret the quantum measurement problem? Several students offered standard responses, regurgitating textbook interpretations without much depth. Expected for a first session. Then I noticed Chen had her hand raised. Yes, Miss Chen. I think the question itself might be based on flawed assumptions, Chen said, her voice quiet but clear. The measurement problem assumes there's a fundamental distinction between quantum and classical realms, between observer and observed. But if everything is quantum, including observers and measurement devices, then collapse might be an artificial concept. Decoherence theory suggests what we interpret as collapse is just quantum entanglement between system and environment, creating effectively classical behavior without requiring special measurement rules. That was actually sophisticated. More sophisticated than I expected from a student, especially one from a species that had barely left their own solar system. That's the decoherence interpretation, I acknowledged. Are you familiar with the mathematical framework supporting that view? Einzellection and Pointer states, yeah, Chen said. The environment acts as a continuous measurement system, selecting certain states as stable while others decohere rapidly. It's mathematically elegant and doesn't require observer-dependent collapse, but it doesn't fully solve the preferred basis problem or explain why we experience one outcome rather than a superposition. She flipped through her notebook. Zurek's work on quantum Darwinism suggests that information about stable Pointer states proliferates through the environment while other information is lost, which explains classical emergence without measurement collapse. But there are still open questions about the ontological status of probability and whether decoherence is complete or just effective. I stared at her. That was graduate-level understanding, possibly beyond. Einzellection, Pointer states, quantum Darwinism, these were cutting-edge concepts that most species only encountered after centuries of quantum research. Where did you learn about quantum Darwinism? I asked. Undergraduate physics at MIT, Chen said. We covered interpretation debates in our quantum mechanics sequence. It's pretty standard material for physics students on Earth. Standard material, I repeated. Miss Chen, quantum Darwinism is a framework developed by our most advanced researchers in just the last few decades. How is that standard undergraduate material for a species that achieved spaceflight 15 years ago? Oh, we've had quantum mechanics for about a century, Chen said. Developed it in the 1920s and 30s. The interpretation debates have been ongoing since then. Decoherence theory came later, 70s and 80s, and quantum Darwinism is more recent, early 2000s. But it's all part of the standard physics curriculum now, a century. They had been working on quantum mechanics for a century despite having no access to galactic scientific communities or advanced measurement technologies. Your species developed quantum mechanics independently. Yeah, we had to, Chen said. We were trying to understand atomic behavior and kept getting weird experimental results that classical physics couldn't explain. So we developed new mathematical frameworks to match observations. Took a few decades to work out the formalism, and we're still arguing about interpretation, but the math has been solid for a long time. Most species develop quantum mechanics only after centuries of spaceflight and access to technologies that make quantum effects obvious and measurable, I said. Developing it independently, on a single planet, using only local resources, we're stubborn, Chen said with a slight smile. When observations don't match theory, we develop new theory. That's how science works, right? The class continued, but I found myself increasingly focused on Chen's responses and observations. Every topic I introduced, she had not just passing familiarity but often deep understanding that matched or exceeded other students from far more advanced civilizations. Relativistic mechanics. She casually referenced frame-dragging effects and closed time-like curves. Cosmological evolution. She discussed inflation theory, dark energy, and the cosmic microwave background with sophistication that suggested extensive study. Mathematical frameworks. She used tensor notation fluently and seemed comfortable with differential geometry. By the end of the first week, I had to reassess my entire understanding of human education. Miss Chen, I said after class one day, may I ask about Earth's educational system? I'm trying to understand how you developed such advanced knowledge. Sure, Chen said. What do you want to know? How much of your education focused on fundamental physics and cosmology? Informal schooling. We get basic physics in high school, usually mechanics and electricity. College is where most people get serious physics if they pursue science degrees. 4 years of undergraduate covers classical mechanics, electricity and magnetism, quantum mechanics, thermodynamics, some relativity. Graduate school goes deeper, usually another 5 to 7 years for a PhD, focusing on specialized research, and this is common. Most humans receive this education. Not most, Chen corrected. Maybe 20% go to college, and of those, maybe 5% pursue physics or related sciences. So it's specialized knowledge, not universal. But we have millions of scientists working on these questions, publishing research, teaching students. The knowledge base builds over generations, and you do this without galactic contact, without access to alien scientific communities or advanced technologies. We do it because we don't have access, Chen said. We have to figure everything out ourselves through observation, experimentation, and theory development. That's what science is. Looking at the universe, asking questions, developing frameworks to answer those questions, testing predictions, revising theories when predictions fail. The process is the same whether you're isolated on one planet or traveling between stars. I thought about that over the following weeks, watching Chen consistently demonstrate knowledge that shouldn't exist in someone from her species background. She wasn't just regurgitating memorized facts, she understood concepts deeply, could apply them to new problems, could engage in sophisticated debates about interpretation and implications. She was, objectively, one of the best students I had ever taught, and she came from a species most of the galaxy considered primitive. The real shock came during a discussion of cosmological fine-tuning, the observation that universal constants seemed precisely calibrated to allow for complex chemistry and life. The cosmological constant problem is particularly puzzling, I explained. Quantum field theory predicts vacuum energy density should be enormous, roughly 120 orders of magnitude larger than observed. Yet our universe has a cosmological constant that's tiny but non-zero, precisely the value needed for galaxy formation and stellar evolution. Some argue this suggests design or purpose. Others invoke anthropic reasoning or multiverse theories. The anthropic principle seems unavoidable, one student offered. We observe these values because we couldn't exist in a universe with different values, but that's not an explanation, another student countered. That's just restating the observation. Why these values rather than others? Could be selection effect from multiverse, Chen said quietly. Everyone turned to look at her. If inflation is eternal, like some models suggest, then our observable universe is just one bubble in an infinite multiverse where different regions have different physical constants. Most regions are lifeless, but we necessarily find ourselves in a region compatible with life because that's the only type of region where observers exist. It's anthropic reasoning, but with a physical mechanism that makes it predictive rather than just tautological. Eternal inflation is speculative theory, I said carefully. Multiverse hypotheses are controversial even among advanced civilizations, sure, but they make testable predictions, Chen said. If our universe is one bubble among many, there might be detectable signatures in the cosmic microwave background where our bubble collided with others during inflation. We're looking for those signatures now. The anthropic principle becomes scientific rather than philosophical if it's embedded in testable multiverse cosmology. She pulled out her notebook, sketched something quickly. String theory also predicts huge numbers of possible vacuum states, like 10 to the 500 different configurations. If all of those are realized in different regions of a multiverse, then our constants are selected from that landscape by anthropic requirements. It's not satisfying philosophically, but it's consistent with both quantum mechanics and observed fine-tuning. You're familiar with string theory, I said, trying to keep my voice level. And its implications for cosmology. Undergraduate courses covered the basics, Chen said. Graduate seminars went deeper. It's speculative, sure, but it's one of the few frameworks trying to unify quantum mechanics and gravity. Even if the details are wrong, the approach of looking for mathematical consistency constraints on possible universes seems sound. String theory. Eternal inflation. The landscape problem. These were concepts at the absolute forefront of galactic physics research, questions that the most advanced civilizations were still grappling with, and this human student was discussing them as undergraduate-level material. After class, I contacted my colleague Professor Yalith, a xenosociology specialist who studied comparative education systems. Yalith, I need to understand human education better. I have a student who knows things she shouldn't know based on her species development level. Define shouldn't know, Yalith said. She's discussing string theory, multiverse cosmology, quantum measurement theory at a level that matches our most advanced graduate students. Her species has been spacefaring for 15 years. Where is this knowledge coming from? Human education is unusual, Yalith said. They developed their scientific method during a period when they were completely isolated, no alien contact, no external knowledge sources. So they built everything from first principles through observation and theory. That created a culture of fundamental inquiry that most spacefaring species lose once they can just import knowledge from galactic databases, but that doesn't explain the sophistication. Actually it does, Yalith said. When you have to figure everything out yourself, you develop deep understanding because surface knowledge isn't sufficient. Humans couldn't just look up quantum mechanics in a galactic library. They had to invent it from experimental observations. That creates educational frameworks emphasizing derivation and comprehension rather than memorization. They teach students to invent physics rather than learn it. They teach students to understand physics at a fundamental level that allows invention when necessary, Yalith corrected. It's pedagogically inefficient by our standards, takes much longer than just downloading established knowledge. But it produces scientists who understand why things work, not just what works. That's rare in the galaxy. I thought about Chen's responses, how she never just cited facts but always seemed to be working from fundamental principles, deriving conclusions rather than recalling them. How common is this approach among humans? Very common in their scientific community, Yalith said. Less common in general population, but their scientific education emphasizes mathematical rigor and theoretical frameworks from early stages. They're also culturally obsessed with asking why, with questioning assumptions, with developing new explanations when old ones fail. It's part of how they survived on a death world, constantly adapting and innovating. They apply death world survival strategies to theoretical physics. They apply death world survival strategies to everything, Yalith said. Constant learning, rapid adaptation, willingness to abandon failed approaches and try new ones. It makes them scientifically creative in ways more stable species aren't. They don't have the deep experience base we have, but they have flexibility we lack. Over the following months, Chen continued to demonstrate knowledge that consistently exceeded expectations. But more than knowledge, she showed creativity in applying concepts to new problems. When we discussed dark matter candidates, she proposed novel detection schemes based on quantum entanglement. When we covered black hole information paradox, she suggested resolutions involving emergent spacetime from quantum entanglement, referencing work by human physicists I had never heard of. Who is this Susskind you keep citing? I asked after one particularly sophisticated discussion of holographic principles. Leonard Susskind, Chen said. Theoretical physicist, did foundational work on string theory and black hole thermodynamics. He developed the holographic principle and cosmic landscape ideas. Pretty influential in modern theoretical physics. On Earth, Chen confirmed. I don't know how much galactic physics overlaps with ours. We developed everything independently, so maybe we're solving the same problems with different notation, or maybe we're exploring different aspects of the same underlying reality. You understand that human physics is likely primitive compared to galactic standards, maybe, Chen said. But we've made progress on hard problems like quantum gravity that it sounds like you're still working on. Different doesn't mean primitive. Just different. We might have insights you lack because we approach questions from different angles without preconceptions from established galactic theories. She had a point. I had spent the semester assuming human knowledge was derivative or incomplete. But Chen kept surprising me with perspectives that were genuinely novel, ideas that hadn't occurred to researchers from civilizations millennia ahead of Earth technologically. During final presentations, Chen delivered a paper on information preservation in black hole evaporation that proposed a resolution to the firewall paradox using quantum error correction. It was sophisticated enough that I shared it with colleagues at the Galactic Institute for Advanced Physics. Their response was immediate and shocked. This is original work, Professor Krent wrote back. Using quantum error correcting codes to resolve information preservation without firewalls or naked singularities. It's mathematically sound and potentially verifiable through observation. Where did you find this researcher? Undergraduate student from Earth, I replied. Presenting final project for my cosmology course, impossible. This is PhD level work minimum, possibly postdoctoral. The mathematical framework alone requires years of specialized study, I'm aware. But I watched her develop this over one semester, working from principles covered in class plus her undergraduate foundation. She's human, from a species we classified as scientifically primitive. The response took longer this time. We need to reassess human scientific capabilities immediately. If their undergraduates are producing novel research at this level, their graduate programs and research institutions must be far more advanced than we realized. Can you put me in contact with Earth's scientific community? I did. What followed was a rapid and humbling revision of galactic understanding of human science. Turned out Earth had millions of active scientists, thousands of research institutions, centuries of accumulated knowledge in fields from quantum mechanics to evolutionary biology to cosmology. They had developed sophisticated mathematical frameworks, built massive experimental facilities, and explored theoretical questions that galactic science had often dismissed as intractable or irrelevant. Why didn't we know this? I asked Yalith during a faculty meeting about the revised curriculum. Because we looked at their technology level and assumed their science matched, Yalith said. We saw they had primitive ships, limited computing power, no artificial gravity or energy shields. We concluded they must be scientifically primitive too. We never considered that they might have sophisticated theoretical understanding without advanced technology to apply it. That seems like an enormous oversight. It's a common oversight, Yalith said. Most species develop technology and theory together. Advanced theory requires advanced instruments to test predictions, which requires advanced technology to build instruments. Humans somehow developed theory far beyond their technology because they're really good at thinking about problems abstractly and developing mathematical frameworks that describe observations they can barely measure. They're theoretically advanced but technologically primitive. They're theoretically sophisticated and technologically developing, Yalith corrected. Their technology is advancing rapidly now that they have galactic contact. But their theoretical foundations were already solid, developed through centuries of isolated research. That's unusual, maybe unique. Most species in the galaxy developed science with outside help, importing knowledge from more advanced civilizations. Humans built everything themselves from observation and mathematics. I thought about Chen, about her notebook full of handwritten equations, about her constant questions and creative insights. She wasn't exceptional for a human, she had said. She was just someone who took education seriously on a planet where education meant figuring out the universe from first principles because there was no one else to ask. Should we revise our curriculum? I asked. Include human perspectives on fundamental questions. Absolutely, Yalith said. Human physics isn't more correct than galactic physics, but it's different. They approached problems from isolation with different assumptions and different priorities. That created unique insights worth sharing. Chen's work on quantum error correction and black hole information might actually advance galactic understanding in areas we've been stuck on for decades. By the following semester, I had integrated human physics texts into my course materials. Students read papers by Einstein, Bohr, Hawking, Susskind, alongside traditional galactic sources. The human perspectives often provided clarity on concepts that galactic physics had made unnecessarily complex through overspecialization. Humans have a gift for clear explanation, one student observed. Their textbooks are more readable than ours because they had to teach themselves, I explained. They couldn't rely on inherited knowledge or racial memory or advanced learning technologies. They had to write everything down clearly so each generation could learn from the last. That created a tradition of clear communication that we've lost through over-reliance on direct knowledge transfer. Chen graduated top of her class and received multiple offers for graduate study at prestigious galactic institutions. She chose to return to Earth for her PhD, saying she wanted to continue the human tradition of independent research before engaging fully with galactic science. I'll come back, she promised. Once I've contributed to Earth's knowledge base. But right now, we're doing interesting work on quantum gravity that I want to be part of. We have perspectives that might be lost if everyone just adopts galactic frameworks, I understood. I had spent the year learning from her more than teaching her, discovering that the primitive species from the backwater planet had sophisticated understanding of universal mechanics that rivaled or exceeded anything taught at the most prestigious galactic institutions. She entered the alien school classroom until her knowledge of the universe shocked everyone. Then we all learned that human education produced students with deep theoretical understanding because humans had spent centuries figuring out physics the hard way, through observation and mathematics and creative thinking, without anyone to tell them the answers. That created sophistication that exceeded their technology level and understanding that surprised species who assumed advancement meant importing knowledge rather than developing it independently. My name is Professor Thelm Vorik, and I used to think educational sophistication correlated directly with species' technological development. Now I understand that theory and technology can develop at different rates, and sometimes the most primitive species technologically are the most sophisticated theoretically because they've had to think harder about fundamental questions without advanced tools to test every hypothesis. Kira Chen demonstrated that principle by casually discussing quantum Darwinism, string theory, and black hole information paradoxes as undergraduate-level material from a planet that had only recently developed faster-than-light travel. That's not because humans are especially brilliant, though she certainly was, it's because human education emphasizes derivation from first principles rather than memorization of established facts. They teach students to understand physics deeply enough to reinvent it if necessary, and that depth produces insights that species with easier access to knowledge often miss. She entered the alien school classroom, and her knowledge shocked everyone not because it was exotic or strange, but because it was sophisticated in ways we hadn't expected from her species' background. Then we all revised our assumptions about the relationship between technology and theoretical understanding, acknowledging that humans had developed one far beyond the other through sheer stubborn determination to figure out the universe despite having no one else to ask for answers.